Welcome to the final part of this week's online lecture. In part 4, we will discuss a few of the applications of rotational spectroscopy. So what are the applications? Well, they are diverse. We've already discussed many of them in the online lectures so far. As you've already seen when we were discussing carbon monoxide in week 5, the precision with which you can determine the spectral lines is incredibly high. You've got information down to the 7th or 8th significant figure. So we know that we have that level of confidence in the value. This is far better than you get with infrared, and far better than you get for electronic. And because we know that the moments of inertia around the axes are associated with the structure of the molecule, through a little bit of mathematical manipulation, we can come up with the structure of the molecule. We can determine bond lengths and bond angles. So the bond angles are just going to depend on the moments of inertia. If we know the structure, then we could also come up with information about the isotopic masses for each of the elements. We can substitute the isotope of one of the atoms and we can get information about that. If it is a natural sample, we can come up with information about the natural abundances of the different isotopes. There will be overlapping spectra and the intensities are going to be proportional to the amount of the isotope that is present. So we can get information for something like this methyl bromide molecule. We can get information about the bond angle and the bond length. We can get information for this molecule here, this methyl acetylene. We can get information again about the bond angle, and we can also get information about the bond lengths of this system, and very precisely. One of the really cool things is the use of rotational spectroscopy to identify and quantify molecules remotely. This is a spectrum not found here on the ground. This is a spectrum that comes from an interstellar dust cloud. And look at the molecules that can be identified. We can identify these molecules because we know very precisely what the frequency is. It doesn't matter if there is only a single line because we know precisely what that line is. We know what rotational energy level the transition is associated with because we can solve the Schrödinger equation. So look at the different molecules that we've got here. We've got some formaldehyde, methanol, sulfur dioxide, carbonyl sulfide, carbon monoxide, sulfur monoxide, lots of different molecules. Here is a more recent picture. This is from an instrument aboard the Herschel Space Observatory, looking at the far reaches of space. At this time it was looking at the Orion Nebula. This is the very stuff out of which stars are made. Stars are being formed in this nebula. You've probably seen pictures of the Eagle Nebula. But this is the Orion Nebula. And look at the different molecules that are being formed here. Not just the ones that I've mentioned. Water is there. We've got carbon monoxide, acrylonitrile, methyl formate, deuterium cyanide, formaldehyde, cations of various kinds, methanol, hydrogen sulfide. All this information is real. All these spectral lines are associated with a real molecule that is in that dust cloud. And a lot of these molecules are organic molecules forming in space. These are the precursors of molecules like amino acids. And in fact, we've seen amino acids in interstellar dust clouds. So one wonders, when these dust clouds collapse through gravitational attraction and stars start forming and solar systems start forming, whether these organic molecules are also accreted into the protoplanets and perhaps we'll potentially see a planet with precursors of these kinds of molecules associated with the building blocks of life. There is some truly fascinating research coming out of this, and this data came within hours of turning this instrument on in 2010. What other things can we do? As Dr. Chan discussed in General Features of Spectroscopy, because we can relate the intensity of a spectral line to its concentration through the Beer-Lambert law, we can do quantitative analysis. That information that you saw with regard to molecules in interstellar space, not only can we identify the molecules there, we can also quantify the molecules there. The other thing, of course, that we can see here is that the intensities of spectral lines are associated with the temperature of the system. The intensities of the lines that you saw in the previous slide are also associated with the temperature of the interstellar dust cloud. By moving the telescope across the Orion Nebula, not only can we identify what molecules are where within the nebula, we can identify the concentrations of these molecules in the nebula. We can identify the temperatures of the molecules in the nebula. We can use that information to construct chemical models and start predicting how these molecules will react together to generate the larger organic molecules such as the amino acids, and then go back and see whether that is true or not. See whether our understanding of the chemistry that occurs there is correct. as I've already said, we can readily distinguish the presence of isotopes in a sample. We can also detect different conformational isomers. Different conformational isomers can have different moments of inertia, and therefore we can identify which conformational isomer we are looking at. And indeed, you can study internal rotational modes within such molecules. You can imagine a methyl group that is rotating by itself within the molecule, and that rotational motion will have a spectrum associated with it. And so you can get information about how fast these methyl groups are rotating in these molecules, and what kind of energy barriers there are associated with that kind of rotation. Now, you've probably heard of the Antarctic ozone hole, I'm sure. This is what it looked like in October 2011. These values associated with yellow and green, these are the normal amounts of ozone we would expect, amounts around 300 or so Dobson units. 300 Dobson units is equivalent to 3 millimeters of ozone if we brought all that ozone down to the Earth's surface. And it's linear, such that 200 Dobson units would be 2 millimeters thick, and 100 Dobson units would be 1 millimeter thick. You'll agree that that is not much ozone, but it is enough ozone to absorb all the ultraviolet radiation from around 240 to 310 nanometers. However, notice what is going on in the center of the Antarctic continent. Notice that the values in this region are getting below 100 Dobson units, so over 2/3 of the ozone we would expect has been lost in this area. In fact, we measure more ultraviolet radiation in this region in Antarctica during springtime than you would measure in Los Angeles. That is how much ultraviolet radiation that is getting through because of the loss of ozone. What has this got to do with microwave spectroscopy? Well, one of the reasons why we understand the ozone hole has to do with the fact that one of the measurements that was first made back in 1987 was by a microwave instrument that made measurements of chlorine monoxide. Philip Solomon built an instrument to look at the microwave radiation coming from directly above it, and it looked at a particular frequency that was associated with a CLO spectral transition. And this is what they saw. This is an average of 3 days worth of data. This was the first time it had ever been done, and it was because we thought chlorine might be responsible for ozone loss. And this proved it. Well, notice the width of this spectral line. This differs from all the other spectral data I've been showing you because they have been at very low pressures, such that the spectral lines are incredibly narrow. What is going on here is that we've got a broad spectral line, and it's broad because of pressure. We are seeing pressure broadening because of the pressure of the atmosphere where the CLO is emitting. And of course, if you've got some CLO emitting from 20 kilometers, then the broadening will be associated with the pressure at 20 kilometers. But if it is emitting from, say, 35 kilometers, it will be much narrower, because the pressure at 35 kilometers is 10 times less than the pressure at 20 kilometers. So in fact, a spectral line that comes from 20 kilometers should be 10 times more broad than the spectral line that comes from 35 kilometers. Now, we knew from measurements of CLO taken in 1984 over Hawaii with the same instrument that the CLO above Hawaii was from around 35 kilometers. When they deployed this down at McMurdo in Antarctica, this was the picture they got. This spectral line here is essentially the sum of two peaks. You've got a peak here, a narrow peak from 35 kilometers. This is exactly the same size, same width, as the peaks they were seeing in Hawaii. And then there is this peak here, which is 10 times wider, so it must be at a lower altitude, and at an altitude of around about 20 kilometers. Not only is it much wider, the intensity is much larger than the stuff that they were seeing at 35 kilometers. So they measured an awful lot of CLO at 20 kilometers. And this explained the dramatic ozone loss, because you needed the CLO at 20 kilometers, because this is the altitude where the larger concentrations of ozone are normally found. You might argue that this broad feature is perhaps just some background spectral feature, and the spectral information is just this peak at the top. Well, here is the same data as before, with that peak and the broad peak underneath that was measured between the 14th and the 17th of September. This is what the data looked like from October the 8th to October the 12th. Notice that all you've got here is the peak that is associated with 35 kilometers. Nothing associated with 20 kilometers, and that is because the ozone loss has stopped and there's no more CLO around in October. So in September there was lots of CLO at 20 kilometers and very little in mid-October, and this was the smoking gun. This was what really confirmed to the scientists that chlorine was responsible for the ozone loss. The models predicted if this amount of chlorine was present at 20 kilometers, then we would get the kind of dramatic ozone losses witnessed, and indeed this is what was measured. This data is also from a microwave instrument, but this time it is on a satellite. The instrument measures both CLO and ozone, both of which have microwave spectra. The benefit of having the instrument on a satellite is that we can measure CLO and ozone over the entire planet. The data in panels I and L on the right are for the southern hemisphere, and that in the panels H and K are for the northern hemisphere. This is what happens towards the end of August in the southern hemisphere in 2010. So notice that you have lots of CLO and very little ozone. You're beginning to see evidence of ozone loss by the time you get to late September. But in recent years we've also been seeing an Arctic ozone hole. The ozone hole is a springtime event, so August-September is springtime in the southern hemisphere, whereas February and March is springtime in the northern hemisphere. So if we look at springtime in the northern hemisphere, again we've got that very large amounts of CLO, similar amounts to those witnessed in the southern hemisphere. And that has led the first time to an appearance of an ozone hole over Antarctica. And with that cautionary tale, we have finished our online lectures for week 6, and with it our discussion of rotational spectroscopy. Next week we will begin our discussion of vibrational spectroscopy. Thanks for listening.